Welcome to Lecture 3 for Lean for Scientists and Engineers. Today we are continuing on our goal of learning to introduce logic and proofs to scientists and engineers. And we're still in that unit right now, learning Introduction to Theorem Proving, writing proofs in Lean. After this, we'll be getting into functional programming in Lean and tying everything together in provably correct programs for scientific computing. So we are currently on Lecture 3. This is Proofs with Structure, content heavily inspired by Mechanics of Proof by Heather Macbeth. So you will find the links for that. You can find it online with that, and highly encourage. We will only be touching the techniques used and featured in this textbook lightly here and connecting it to science and engineering. Go and get practice by working on the examples and exercises and extra problems they have in that textbook. So for today, we have these things that we're going to be talking about. So I want to recap Lecture 2 and revisit this syntax versus semantics question that we talked about there. We will be doing proofs with intermediate steps and proofs using lemmas. And along the way, we'll see how much we talk about junk values. This is a curious little thing. I didn't quite develop an example. I think we might end up actually hitting this tomorrow rather than today, but we also will be introducing logical operators and proofs with and or. So here's a reminder. We have this survey. I'm going to if you have access to the slides, you can do that. Here, I'm going to pop out of the share screen so I can get this to the attendees. That please, if you're following this content, let us know more about yourself and why you're interested in Lean. And the questions I wanted to ask attendees today are these two poll questions, so I can learn a little bit more about how people are engaging in this material. Okay, just give me 1 minute to set that up. And here we go. So I have launched a poll on WebEx. Are you able to see it? Is it showing up on your end? How many hours did you spend with Lean last week? So if you attended both of the lectures or listened to both of the recordings entirely, then that would be, 2 to 4 hours or 4 to 6. You can pick what you say. And if you did a lot of exercises outside of that, you can cast your votes. Or I was asking one of my students what was theirs before they were like 40 hours. I'm like, yeah, you're helping me put this content together. So we greatly appreciate them. I'm not doing this on my own. All right, sounds good. Looks like we're getting votes in. Can you see the other votes, people? I'm curious. No, you can't. Oh, okay. Well, I'm going to take a quick screenshot for my own benefit. About a third of you are saying 2 to 4 hours, and about a third are saying 6 to 8 hours. And the next block of time is 8 to 12, and one person is saying 20 plus. So sounds good. You will get out of this what you put into it. That's just how class works, generally speaking. This is also a not for credit class. I'm not actually assigning any proper homeworks or giving assignments or grading things. So it really is what you put into it and emphasize. But the direction for you, if you haven't done any more than just tune in, I mean, it's fine if that's all you want to do, but I can pretty much assure you, you're not going to learn lean without practicing, without drilling into this stuff on your own. Okay, thanks to those who voted. I'm going to hop into another one. Did you explore more mechanics of proof exercises from chapter 1? Just again, curious how much people are engaging with this. Hey, I like this. We got a few people who said I solved them all. And a few people who tried one or two. That's a big step. Those of you who said nope, I really challenge you to move up to trying one or two. And if you're hitting difficulties with these, then come to Zulip and ask questions, saying, I was trying to solve this and I got stuck. And I or somebody else is happy to help close those gaps in understanding and help you continue in learning lean. Recognize you're trying to learn two things at once. If you're new to proofs in general, you're trying to learn math proofs, which itself is a hard thing, and you're trying to learn how to do proofs in lean, computerizing them. So keep working at it and keep challenging yourself. Spend your time with this material and ask questions, get help, and you'll learn, you'll grow from this. It's all good stuff. All right, thank you. All right. You know what? For the sake of the recording, I'm going to cut that part out and jump back to slide 1 and go over that one more time so everybody who eventually sees this on YouTube won't have to deal with that. So welcome to Lean for Scientists and Engineers. Thanks for coming to lecture 3. We're excited to continue on with the schedule, which today is going to be proofs with structure. Great thanks for Heather Macbeth for developing the mechanics of proof content and textbook. Today, we're going to be surveying attendees and then recapping syntax and semantics from lecture 2 and going on with additional strategies for solving more complicated proofs. Instead of just using calculation-based things, we will include intermediate steps and proving with lemmas from Mathlib. And we'll wrap up with logical operators and proofs that use and or. So here's a slide from last time. This is defining or reminding you what syntax versus semantics is in natural language. That I can combine all possible combinations of words to make sentences, and if I don't pay attention to subject-verb agreement, or if I don't pay attention to things, I might end up with grammatically incorrect sentences, and that's wrong. That's a violation of syntax. But if I satisfy grammar just fine, then I end up with grammatically correct sentences, and of those, we have meaningful and true sentences, which have a connection from not just the world of language, but to the world of reality. And these are true or false about entities in real life. And this is what I think your first step in understanding what these two words mean. Syntax is about grammar. Semantics is about meaning. Now, there's another level up where we talk about what does this mean in terms of logic. So I would say all possible combinations of logical symbols, if I get the syntax correct there, this maps to logically valid statements. And those now are things that are stuff we could check with a theorem prover, stuff we could check with mathematics and logic. That's going to be valid statements, but they don't have any connection to the real world. To do that, we need to bridge the realm of language to the realm of reality and have statements that are true or false about entities in real life. And so the vocab word becomes sound. This means the arguments are valid and also have true premises. So I showed this slide last time, and we had a lot of discussion around this, and today I'm going to revise this and make it better than last time to show these kinds of ideas in a little bit more precision. And so this is the way I'm going to set it up this way. We have an additional tier here. So now we have scientific models exist as symbolic models and computable models. And we also then have code to represent these in scientific software. And a helpful comment from one of the attendees was talking, well, there are symbolic models that can be compared to reality. If I would have something using propositions, we'll get to some of those later in this lecture. And so you'll see some examples of things that just use logical statements. This is true and that is true, therefore this and that are true, for example. And those could maybe directly be connected to reality as a purely symbolic model. But most of the time in scientific computing, the things people do to simulate molecules and the weather of the planet and microorganisms and space, these are computable models that rely on often large pieces of software that people have developed. And people write down these computable models after converting them from symbolic models that usually use things like differential equations, calculus, other types of math things that need to be made into approximations that a computer then can run a simulation on. So that's why we have lines going between these. And traditionally, the validity of mathematics and the scientific theories themselves, this is all established by hand. Traditionally, someone is going to say, here is my math. And they're going to write it up in a piece of, in a research paper and saying, I have a brand new thing. And maybe it's not written pencil and paper, but like they're typing it up in LaTeX. The computer is not checking whether or not this is correct. You can easily have a typo in your derivation. You can easily have a logical misstep that you don't clarify while you are either developing your theory of this, or whether you're going to say, I'm going to develop an approximation of my theory so I can turn it into software. Then when you are a software engineer, you're going to say, it's time for me to build my code to run on a supercomputer to simulate the weather. And you're going to say, well, I want to build my things off of the computational fluid dynamics, that things flow in and out of one parcel of air, for example, and I'm going to do my best to translate what I understand to be the handwritten models in the literature into something that's a piece of code. I've translated something human readable into something machine readable, and then the code runs and we want to compare this to experiment. I say various automated and manual means, okay? Because sometimes you might have some database of experimental results and you're going to say, I'm going to run my code and just check the numbers of my code outputs versus that. That would be an automated way to do it. But I mean, the construction of that experimental data involves some manual things. Sometimes we don't even do that. Sometimes I just set up in my computer, like I'm going to run my simulation under these conditions. We do a lot of molecular simulations. So we'll say, what is the vapor pressure of water at 100 degrees Celsius? And I'll do the simulation and I will say, look, my vapor pressure is 2 bar. Okay, we're off. It should be a lot closer to 1 bar, but I was off by a factor of 2. So I have, in that step, by getting the results, looking at the results, I've compared my code, my simulation run to reality in some sort of way. And that's a sort of manual check to compare to experiment. To summarize our goal and our aim in all of this, and we're not here yet, but we're targeting this as our vision, is can we represent this entire world in Lean? Can we validate the construction of the math itself? Lean is already doing this. Okay, Lean, Mathlib, the mathematicians and computer scientists who've been building Lean, they're very much doing this already. But can we add Well, and I would say people are also working on connecting the math to the code itself. So there are people doing just computer science related program validation that doesn't necessarily connect to science. So that's sort of skipping the second tier, and people are also working on that. We're also interested in this additional layer of defining scientific models and then tying everything together in one system. So that is the vision that I was also describing in lecture 1. And we're not claiming to bridge this gap of connecting this to the reality, because that's a different sort of question. And I think it's actually really helpful to, we'll see this a lot more when we get to the functional programming in Lean, that input and output in Lean is treated differently compared to theorem proving in Lean or dealing with internal Lean objects. Because as soon as your code starts interfacing with the real world, it becomes a lot harder to prove things about it, because the real world is unpredictable in ways that the realm of math that the computer program is operating in is predictable. And we'll talk about that more later, but this is to clarify syntax and semantics and some of those bridges there. There's a slide I didn't include that now I feel like talking about. Let me pull that out quickly. It is, oh, yes. So we'll be talking more about this later. This is our current proposed way to be bridging this gap of running calculations in the real world, running computable stuff over floating point numbers versus doing math proofs over real numbers that exist in the realm of the theory, in the realm of the model, in the realm of the computable functions. Okay, and talked a bit more about that in lecture 1, and we'll be also addressing that more in the second half of the course. All right, so next, let's get back to proofs. So we have proofs using intermediate steps. This is moving into chapter 2 of Mechanics of Proof by Heather Macbeth. And in general, sometimes it's helpful to prove a little thing that helps you to prove the main thing. So I illustrated with this some blocks. Maybe you can't go all the way to the top until you start constructing everything up from bottom up and build up a fancy proof. And this is at scale how Mathlib works. Mathlib is this massive interconnected web of proofs. We have over 150,000 theorems, and they build on each other. And you use smaller proofs in order to build bigger ones. Or you use more fundamental, more simple proofs in order to build ones that depend on those. We can also internally define a statement within a theorem and then prove it quickly and then move on. So we don't necessarily need to have everything interconnected. If I'm proving a new statement, I don't necessarily need to put it out in the database and say, now everybody can use this if they want to. I can just say, for the time being, let's internally define a statement and prove it. And I have a link to a GitHub repo to show what this looks like at scale. Okay. So this is a proof of Kepler's law from Newton's gravitational law and equations of motion. So I'm not going to go into huge details of this. You can parse this yourself a bit, and there are probably ways to make this a lot shorter by being clever with things. But You can see this is a really long proof. So we have several hypotheses coming up in front, and then we say these are all of our premises, and then we're going to prove that the square root of 4 pi squared times d cubed divided by g times m1 plus m2, this is a statement of Kepler's third law, that this follows from all these other things that involve defining a center of mass, defining a distance between two bodies. This might be the sun and the earth, or the earth and the moon, or two different stars, for example. We have the gravitational force, the centrifugal force, force balance, and the definition of a period. We also have constraints. We don't have mass never takes a negative value, for example. Distance never takes a negative value, and so forth. Period, we don't have a negative period. And my student was really struggling with setting this proof up. She had learned a whole bunch of mechanics of proof, was working through these calc blocks, and was just struggling to set it up where you would say P is equal to stuff, the period is equal to different things, and how do you rearrange? How do you get that done? And we asked a question for some help, and someone on Zulip mentioned, how about we try to prove this intermediate statement first? And we have a have statement. So that's the tactic we're going to introduce today, is this have statement. And what this does is it basically sets up, let's prove something else first. After we have this, we can use this thing and it will make our lives easier down the road. This still took a lot of effort to close all the proofs. We'll talk about some of these techniques in a little bit, but before we introduce this intermediate proof, we weren't able to make much headway. I have a question. And it is, does Lean 4 have built-in support for units of measure in order to avoid adding 2 kilograms and 3 meters cubed, for example? Or if you multiply 2 meters per second with 3 seconds, it automatically knows the measure as well, 6 meters. Excellent question. Short answer, no, it is not built in. There are discussions on Zulip about this. I have a couple students who built a prototype of a thing defining dimension, but not units. Units are different from dimensions. So units would be kilograms and meters squared, as this question is, but dimensions would be mass and length. And so we also, with units, have additional issues of like adding meters and millimeters, versus adding length, and length is always is a bit more well-defined and less complicated. And yes, we can define this because it's a set of math, actually, and we can prove neat things about this. But it is not yet fully functional in Lean. It isn't necessarily going to be packaged with Mathlib either, because that is explicitly something that is outside of pure mathematics. The generalized version of what dimensional analysis is an abelian group, and you could write theorems about it that might be useful for those things, but specifically saying, I want this to deal with my familiar units like length, mass, time, luminosity, electric current, things like that. That kind of specialization is going to be something that's outside of Mathlib that we would very much include in something like, let me show a familiar slide again, in something like Scilab, a database of formally verified science. So that would be something very useful to include in this to prevent things like that and so on. Okay. So now we're going to hop over to Lean. Okay. I need to move my chat window. All right, here we go. So the first is introducing the have tactic. This is proofs using intermediate steps, example 2.1.1 from Mechanics of Proof. I will actually pull out this example in Mechanics of Proof briefly here. So more typically, proofs will have a more complex structure. And the problem is let a and b be real numbers such that a minus 5b equals 4 and b plus 2 is equal to 3, show that a is equal to 9. So previously, this was solved using a single long calculation. A is equal to a whole bunch of things. And you look at this and you're like, well, I can use the method of staring and find out that b should be equal to 1. So maybe it would be helpful if I just came out with finding my solution to b and then plug that in to my calculation with a, and I can use that in here. This is closer to how we often solve problems in using high school algebra methods, for example. First solve for b and then do substitution. So the idea is you will be deducing the fact b is equal to 1. I shouldn't scroll so fast. We need to start with this statement, b plus 2 is equal to 3, and deduce that b equals 1 follows from that hypothesis. So the approach in Lean, and I'm going to hop over to VS Code so we can see this live, is I'm going to start with H1. I'm assuming H1 and H2. And then I start with my goal, and I have this as my info view. A and B are, let me increase font size for everyone. A and B are real numbers, and I have H1 and H2 as hypotheses in my scope, and I'm going to conclude that A is equal to 9. The first thing I'm going to do is introduce have. And have is going to introduce a new hypothesis named HB, and I define it as b is equal to 1. And I'm going to say, how do I define this brand new hypothesis? I need to give justification for it. And here I'm just going to use the linearith tactic to do so. And after this have statement, we can see what the new status of the proof is. Now I have a new hypothesis, HB exists in the scope, so I can use it. I didn't lose anything, I just added something to my scope. And so that's helpful. I have a new fact at my disposal. So now when I step into this calc block, I can set up A is equal to A minus 5 times B plus 5 times B. This is going to be solved by ring. So we were doing some examples like this last week. And now I do substitution. I replace A and, I replace B using I'm going to replace the first part of this with 4, A minus 5B times B. I'm going to replace that with H1 first, so this gets replaced with a 4. Then I'm going to replace the B with a 1. And finally, we're going to simplify this just using ring. We could use norm num. There'd be different ways to close this goal. So that's an illustration of the have tactic and how it works. So something that you might be thinking about is I went to this have tactic, and after this have tactic, I have a new statement in scope. Why wouldn't I just start out by adding this hypothesis B1 into my example? That seems easier, right? I can just put that up here in the front. And indeed, if I do that, I can now skip the have statement and I can continue with exactly the same set of calc block, and I prove this and I close all the goals here. We do get an underlined warning here. It says unused variable H2. Okay, so we're not actually using H2 anymore. We're only using HB. And this is So again here, I start this and I have a is equal to 9. I need to prove that, so I set up my proof and I go forth. So what's really different between these? Should I use have or should I be adding a hypothesis? What's the difference here? And this is what I just showed you. I'm putting these side by side. Number one, we've actually changed the theorem statement. I'm not proving the same thing that I set out to prove the first time around. If I was very particular about what I wanted to prove here, well, now I've changed my theorem statement, so that's might be deviating from what I was wanting to do. That's not necessarily a deal breaker, though. If you think to some of the problems from last week where we were talking about, so I have an airplane. It's traveling in this direction, it's traveling that other direction. So, I set up my problem. I'm just trying to define some type of context. Maybe it's up to me to define the theorem statement however I want to do. So why might this still be a bad idea? Well, H2 is unused. That's just clutter. Okay, we could delete this. And mathematically, the hypothesis, this theorem statement would prove just as much as it would before. But the main problem with this is we don't know if HB is true. In the previous version, I know that HB is true because I introduced it as a have statement and then I justified it. I proved that it is true, so now I can actually use that, and that's safe. See, I can define absolutely whatever I want in this place, but I can only move forward if I do that. So let's try this. Have b is equal to 2. I can't do that. B is equal to 2 fails, it will say Linnerith failed to find a contradiction. It proved false from this. Like, this tactic tried solving it, and it ended up concluding that, well, this statement is not true. B equals 2 does not follow from H1 and H2. That's the safety check here. I can't just go and define anything that I want and put it in a have statement. I can go and define anything that I want and put it into a theorem statement. We're not going to, yes, this proof step doesn't follow anymore. Well, that's not quite a good thing. I'm going to jump to back to the slide to say why introducing a contradiction in your premises is such a bad thing. And this has a name. And yeah. So if HB contradicts any other premises, we're in real trouble. And the reason for that is the principle of logical explosion. You must not assume a set of premises that contains a contradiction. This is referred to as the principle of explosion. It has a few different names, logical explosion, things like that. And there's a very lovely Wikipedia article on this. Also it's referred to as proving false. The reason, there's some mathy reasons for that, some lean reasons for that, but that was actually what was happening right here when I put the cursor here. Assuming all of these things, therefore false. We have proved false from this. We've introduced a contradiction, and that's the concern there. And so if let me jump back to the principle of explosion. This is a lovely explanation of this. I also like the Latin name for this stands for I'm getting a mind blank. Ex falso quod libe from anything from false anything or something like that. Okay. Well, I missed that. All right, but okay. Here is an illustration that I think is just helpful to, if this is new to you, I found this illustration particularly helpful when I was encountering this for the first time. Let's assume two statements. I'm going to assume that all lemons are yellow, and I'm going to assume not all lemons are yellow. These obviously contradict. I can't have both of these things be true, but I'm going to suppose that both of them are true. That means I can use these as evidence to prove other statements. So now I can prove unicorns exist. And here's an argument that does that successfully. Not all lemons are yellow is assumed to be true. All lemons are yellow is assumed to be true. All lemons are yellow or unicorn exists must be true. And we're going to get to logical or later in this lecture. But we know an or statement is true if just one part of this is true. So I know this two-part statement is true because the first part, all lemons are yellow, has already been assumed. So I know this two-part statement is true, and now I can carry on. Okay. Well, I'm going to use this thing that I just proved. All lemons are yellow or unicorns exist. That is a statement that I can use in conjunction with not all lemons are yellow to prove the second part of it, unicorns exist, because I know the or statement is true. And that's this idea, is I can follow this procedure over and over again to prove that unicorns do not exist. I just need to change the content of the or statement. I could prove anything. So there's an explosion of true statements. That's this thing. An infinite number of statements. I can come up with any well-formed formula that I ever feel like writing down, and I'm going to be able to prove it from just a pair of contradictory premises. So if you are building a large database of things that you believe to be true, you can't have any two of them contradicting, because that will lead to a principle of explosion. So this is relevant to scientists and engineers because it's often up to us to define our theorem statements. It's up to us to define the objects that we're working with, and we need to be extra careful not to introduce contradictions there. So someone not very familiar with theorem proving might say, oh yeah, it'd be great if you can prove everything, but that doesn't actually help. There is a tactic that Lean has. It's called slim check. And sometimes this is useful for detecting contradictions by searching for counterexamples. And there are a bunch of examples here on how to use slim check. I'm not going to go into this too much, but I did put in one example here showing how this can work. So here's a very simple case. A minus b is equal to a plus b for natural numbers. And I'm saying this is true for all natural numbers a and b, but this is not going to be true if a and b are anything but 0, really. And so I'm trying to use this statement to prove that a is equal to 5, and I can invoke slim check to find problems. And it was able to find a contradiction in this case. I tried with the example that I set up to run slim check, but this one tried 100 times before giving up. It's searching for a counterexample among variable assignments for a and b, and it didn't find it. That doesn't necessarily mean it doesn't have any contradictions, because I knowingly introduced one by saying b is equal to 2 instead of the correct answer b is equal to 1. But that's a long explanation for basically why I guess some of the hazards of keeping track of contradictions in your theorem statements, if you would, and then also why you shouldn't just go put things into the assumptions. You need to be careful. One of my students was trying to prove a very hard thing to prove, and in the end he was like, well, what if I just put something up in the assumptions? Then I can use it and I can carry on. And he thinks that's true, but he didn't prove that it's true, and it's technically not true, and so there was a falsity, and so he ended up proving it, but we can't trust that proof because the theorem statement can prove anything, so we can't trust that. We can only do that if we don't have any false statements in the background theory. All right, so next is using existing lemmas. So here we have, in mechanics of proof, okay, so I'll just recap a bit. Okay. Oh, I need this one. Okay, so mechanics of proof, we just wrapped up chapter 2.1, intermediate steps. So you can see we did one example. There's 8 more you can look at, and you can dig into these. This will help really train your theorem proving skills, okay? You'll get a lot of practice, how to set these up, how to think about these things, because what kind of intermediate statement do you introduce? There's strategy that gets involved with that sometimes comes with practice, that often builds like that. So work through the examples, see some more cases, and continue on to the exercises and learn some more about that. Okay, next is invoking lemmas. And invoking lemmas is going to bring in this idea that you have other things you know are true, and you're going to use that information specifically in solving your theorem. Mechanics of proof talks about the apply tactic. So we're going to talk about how to use apply. This is a relatively simple way to bring these. You have a goal, and the goal is of a certain form. Then you go and find a theorem that says, if I have something of this goal, I can turn it into some other form. And that might be the other form that you're looking for. It might be your final goal. So you can go and get that theorem. How can you use that theorem? It's because someone else proved that theorem to be true. This is where you can start using things that are well beyond your own math ability because other people prove these things true. And as long as you can line up the goal with the theorem statement, then you're going to be able to prove this just fine. There's also using existing theorems through tactics. Some of the tactics are aware of a bunch of theorems already, and some of these really, really high-powered ones might be linked up to hundreds or even thousands of theorem statements, and those have been proved, all checked by Mathlib. They use some automated sort of means to check and to identify what's going to be relevant and close the goals in following their recipe, okay? Other times, the tactics don't know about the theorems right away, but you can tell them about theorems, that they have an ability to, you can imagine maybe you have a theorem that has a tactic that has access to 100 theorems, but it doesn't have access to a theorem that you know would help it to solve the problem in this context. Well, you can add that theorem to its context of 100. Now you have 101, and it can make progress on the goal because you've given it a useful theorem to solve. All right, what does that look like? So first we're going to look at 2.2.1 from mechanics of proof. And we are trying to solve this problem where we have a curious kind of goal, which states that x is not equal to 1. This is a negation. And we haven't addressed with, we've done equality, we've done inequalities, but we haven't done with does not equal before. And I want to, if I try norm num, you'll say it doesn't do anything. I can say that, okay, well, I started with x not equal to 1. Right after I did norm num, it changed it a tiny bit. Okay, and this is the not symbol. We'll talk about that very soon. When we talk about how to read these math symbols, I have a logic section later in this chapter. Okay, but this means not x equals 1. Ooh, it's hard to see on the screen. Oh, it's easier to see on the screens in the classroom. It's harder on my laptop screen, but when I put my cursor over the equals sign, we can see that x equals 1 is in parentheses, essentially. This is a proposition, and we are negating this whole proposition. But bottom line, it didn't close the goal. It left it here, and it didn't solve it. Um, so we can't use norm-num, and there are other tactics, more powerful ones that can close this, like linarith, but that's not the point. So we can't close it with norm-num, but there is a way to clean up this proof. And the way is by changing this proof goal from a not equal statement to an inequality statement. And not, so NE underscore of LT, if I put my cursor over this theorem, it will basically show me what the theorem statement is according to the documentation. And it has a bunch of these words. We have alpha, type U, pre-order, A, B is alpha, H is A less than B, colon A not equal to B. Okay. So something, as you're brand new to this stuff, you looking at the documentation, a lot of this stuff doesn't necessarily make sense. What does type U alpha, what is a pre-order? I don't know what any of these things mean, but you can get a hint, I think, by looking at the last part of the statement. These are sort of around the scope of the different types that this holds for. This holds for both natural numbers and real numbers and things, but we're talking about A is less than B implies if this is my assumption, I can prove that A does not equal B. A less than or equal to B includes A equals B, but if I know that A is less than B, I'm certain that A does not equal to B because it can't be equal because of how less than sign works. So this is going to be something that I can use to turn my A does not equal to B into a is less than B goal. So what we've done is we've gone and we've applied this, and you can see before I do the apply, okay, I have x not equal 1. After I do the apply, I've turned that into x is less than 1. So that's what apply did. I already know that this theorem is true because Mathlib has checked that, Lean has checked that. So I don't need to justify my change of the not equals to the less than because the theorem itself is the justification. Then I proceed and I go and do a calc block, again using techniques that we learned about last week on Tuesday. And here, I'm trying to prove this, and so I can use a combination of ring to rearrange, rewrite to substitute the value of the left-hand side in for this inequality, and I have a final goal of 2/3 is less than or equal to 1, and this can be solved by norm-num, so we're able to close the goal. So that's a simple way to bring in a theorem from Mathlib. Another thing to really keep in mind, and this is something that we all that we will often struggle with. This one came up with in an example that we'll be having at the end of class when one of my students was trying to set up a problem and dealing with real square root. We have a question alpha. What does alpha mean? Okay. I'll address that before I move on. I'm putting my cursor here. We're talking about this alpha. Oh, can't put my cursor over it. It stands for a generic type. And I said I would just address this now. Someone in the chat maybe can help a little bit, but we're going to actually be saving types for next week when we talk a lot about more about types. In this, so far, we've only been talking about the basic numerical types. I believe I had that in lecture 1. So what is a type? Oh, no, must have been lecture 2. No, it is lecture 1. Well, okay, no, bottom line, we will be addressing types in more detail, but yes, it's just a type in a universe. Those are some lingo about how Lean's plumbing works, if you would. What's sort of going on behind the scenes in order to make the type theory. If you're really interested in those aspects, there's actually a different textbook that we're not going through called Theorem Proving in Lean 4, which gets into the nitty-gritty of those a bit more. Good question, though. We can dig in deeper. Okay. Yep. Yeah, true. And there's a comment from Simon Beaumont. Theorem Proving in Lean deals with it fairly early on. Yeah, you'll get it in, I think, chapter 1 or 2, right in there about what types are, what universes are. We're going to be hitting those next week when we get into proofs about functions. We're going to talk about those in depth. Okay. Now, Lean is not a calculator yet. Okay, so it doesn't, NormNum doesn't know how to handle the above thing that, I mean, obviously, 3 times x equals 2. I kind of know that this is not equal to 1. All I need to do is calculate what is x equal to. And then I can compare those two numbers, and I'm very quickly certain of what it is. Or I might say, well, what is the square root of 2? The square root of 2 is 1.414 something. That's obviously less than or equal to 3. So if I can start getting a decimal representation of some number, those are easy for us to get, but it can be hard for Lean to do because it's not a calculator. It's a theorem prover. And there is present efforts to build more powerful tactics that would do calculations in a rigorous way. We often, if we struggle to find things, may need to give it some help, may need to play some tricks. And in this case, NormNum can't solve this, but I can if I give the NormNum tactic a helpful theorem. And this helpful theorem is that, I'm going to sit still here. Oh yeah, okay. No, I'll move the mouse carefully. Okay. The square root of x is less than or equal to y. This, we'll talk about this symbol. This means if and only if. It means we can go to the right and to the left. They both imply each other. This implies that y is greater than or equal to 0, and we'll talk about this character very soon too, x is less than or equal to y squared. If I can turn this thing about square roots into something about x is less than or equal to y squared, it's no longer about x as a square root operation on x, which itself is irrational and weird, but it just deals with the squared operation, which maps down to the rational numbers and is easier to deal with. And so NormNum can handle things about powers of numbers. It can handle things about x and y squared. Okay. It can't handle things about the square root of x. But because I can go into Mathlib and I can say, hey, we proved that this, somebody proved that this is true, I can give it one extra bit of a theorem. It adds that to the theorems that it checks might be useful to it solving this goal, and it can do this now, and it couldn't before. So this is a question that often comes up. Why doesn't norm num, why doesn't it just check this every time? You know, if somebody built norm num so that it checked it included this, then I wouldn't need to add this. Someone would have engineered the norm num tactic so it just uses it automatically. I wouldn't have to worry about that. And the answer, is, excuse me, efficiency and scope creep. So we've talked before about all the different kinds of tactics that we have. And these tactics they have a purpose, so to speak. I can close, I can prove this, okay, using linearith. I cannot prove this using norm num. Why would I have a norm num if I have linearith? Well, linearith is more powerful. Linearith is less efficient. It tries more things. And sometimes there's not overlaps too. You know, sometimes maybe some simple problems involving numbers you can solve with maybe 3 or 4 different tactics. But if you move to numbers and variables, now you can solve now half of them apply. And if you have inequalities versus equalities, then some of them different apply. That's this idea of scope creep, okay? When people write tactics, they have in mind a very clear purpose for them, and they shouldn't really be doing things outside of that. If you need to do something outside of that purpose, you would have a different tactic. Maybe that other tactic would do more powerful things, and then it would call the simpler tactic. That totally happens. There are tactics that just search the entire Mathlib library to find something and then use it, okay? But you're not going to use that one if you need something simpler. That's not so efficient. So those are the 2 main reasons why you need this. But, okay, in a pinch, okay, you don't necessarily need to use a high-powered one. You can use a simple one and add one very useful theorem that you know is going to be helpful for this. That's a very efficient way to direct the proving of this approach. Right. So now we come to some really, really big questions. And these are questions that I find are really, really hard for scientists and engineers to answer because the answers aren't easy. Okay, so I have 2 slides here, and you can look at them in detail. There's all these sorts of links and so forth in the slides you can look at. The first one is how to find tactics. The second one is how to find theorems. So to find tactics, keep learning them one by one. Okay, these are rich things. They do stuff, and it's up to you to decide which ones to bring into a given context. And so the way you can do that is just by doing more practice, by learning. You can also read their documentation after you understand this to a little bit better and can navigate that bit of code, for example. You can also find lists of tactics. So mechanics of proof, mathematics, and lean, these have lists of tactics that they use in the book. So go to these indices, in the indexes for these textbooks. You can find lists, and if some look unfamiliar to you, go and learn about them. People have also created tutorials. I just have 2 here. I know there are more, so if you have, I can update this list if you know of someone who's developed a useful cheat sheet, so to speak, of different tactics. And these look like so here's the one from is it Martin Dvorak, who's very active in the lean community, made this. He calls it a spell book, which I love that I love that. Like here's a bunch of things. These are magic spells of sorts. You use them in different circumstances to do different things. And it starts with a helpful covering logical symbols. We'll get to that in a minute. And then says what kinds of, if this logical symbol is in a goal, try these tactics. If it appears in a hypothesis, try these tactics. And there's a bunch of generally useful tactics as well. And this is the tactic, and this is the effect that it has. And so on. So some of these we know already. Rewrite expression. Okay, we use rewrite to do substitution. We can put a backwards arrow here, depending on the shape of what we're looking at. Calc. We've been learning calc. Calc is a tactic that we've been learning how to use. This sets up a proof by calculation, a sequence of propositions that when combined together using transitivity will prove the goal, and so on. Some of the ones here that are particularly clever as well as expensive are the ones that end in a question mark. So the ones that end in a question mark search for lemmas that can do a thing. So if I'm trying to do an apply, if I have a goal and I just need to find a lemon whose conclusion exactly matches the goal, then can I just apply question mark? It will search through the lemmas in Mathlib, and it will go, and if it finds one, it will say success. Exact is similar. It will try to do that. We can try rewrite. Can I do a rewriting a simplification of the goal using different things? Okay. And I love Aesop. Try to solve it using magic. This one's a really powerful and expensive thing that just tries to close the goal. One of my students uses this a lot to close the different theorems that we state for science and engineering. You can put question mark to unpack what kind of magic was used. Sometimes this is unreadable, but often it will highlight the names of relevant lemmas. So maybe you can look at those and say, ah, that's the lemma I was looking for. Now maybe I'm going to clean this up so I don't use the expensive magic spell. I can just write it simply using the useful lemma that it found and write it out, prove it myself. Okay, so that is one. I'm going to also bring up from my student Colin Jones, who created this list of useful tactics as well, and has some examples to show how these work. So you can take a look at these and learn and get some ideas. And again, though, it comes back to this first thing, keep learning them one by one. It comes with practice. I mean, just like with doing magic, you have to practice your incantations in order to figure that out. Okay. Oh, and finally, all of these are, I don't know how to prove it. How do I find a way to prove it? But sometimes we have a tactic in hand. I have a proof in hand, or I found something in Mathlib, and I don't know what is happening. So you can always put the mouse over your code in VS Code, and you can see the documentation in the examples. All right, so that's my advice there. Good luck. The next one is how to find theorems. And again, it's keep practicing. Here, the main suggestion is to search the Mathlib documentation. That if you go to the Mathlib docs, you can go up to search, and you can go and try to find stuff. What this means is you are searching for the name of a theorem that is kind of like what you're trying to prove. So if I come back to this one, What's the name of this theorem? It's not equal of less than. NE of LT. Okay, that's kind of what it means. It's following a naming convention that is very commonly used in Mathlib, and the more theorems that you end up looking at, the more use to this notation you'll get. Here is another theorem. It is real dot square root less than or equal to if and only if. Right? So it's a naming convention that's pointing at the less than or equal in the if and only if. That's the name. But I mean, how do I know that it's named this? I mean, maybe you don't. Okay. But we found that one because we were trying to prove something. And so we tried real dot square root. And I've got a whole list of these. Which one? Well, there it is. Is that the one? Let me see. Oh, no, square root less than equal if and only if. So it's real dot square root. Here it is. Okay. I had to scroll down a bit to find it. But it's definitely not involving division. It definitely doesn't involve non-negativity or square root inverse. Okay, so I can skip some of these before I look, but maybe I want to look at less than equal square root. Maybe look at that one first. Okay, I open up the documentation. I can see this is the statement. X is less than or equal to the square root of y. X squared is less than or equal to y. Oh, maybe I would have used this. Okay, but that's how you search the Mathlib documentation. You find a theorem, you open it up, you take a peek at what it says, you judge whether it's what you're looking for, and if it's not, then you keep looking. That's method one. And I think among intermediate to expert lean users, this is the biggest way to do that, I would say, is this takes some skill to learn to navigate these things, but this is the most mature way that people end up finding these things. There's also Moogle. Moogle is a fun website. This is, you can describe what you're trying to look for in natural language. So you go to moogle.ai and maybe I just want to find pi. How do I define pi? I can just search for pi. And well, the first one isn't what I'm looking for. But real.pi. Pi as a real number looks good. Now I have it. And this is a definition of a thing. And we have the documentation and a link to the source code. So I found pi. This is useful for searching for theorems as well as definitions. So you can find both of those in that way. Or is it just for definitions? Maybe it's... Oh, no, it's for finding theorems too. Yes, that's right. That's right. Moogle is the lean Google. Another tool, but I would say this is less helpful for finding things like what I just shared, where I know fairly specifically what I'm looking for in terms of less than inequalities, things like that. Moogle is great for finding named things that maybe I know from outside of a lean context that I want to find out where it is defined in lean or how it's proved. Just try them, learn how they get useful for you. Where there's a link to what Colin Jones created, a list of useful lemmas. He's been developing proofs in science and engineering things for about a year now. And here's a reminder of useful tactics to deal with things, and then check it out, okay? A bunch of theorems involving addition and subtraction. A bunch of theorems involving multiplication and division of things. And so if you need to do some of these things as you're rearranging your complicated algebraic expression, well, these are things that you will learn, you can invoke and you can use and apply them as you encounter the same kinds of things over and over again. You'll get used to using muldiv cancel. This is a big one because often we want to take x times y divided by y is equal to x. Well, I can't do that unless I know that y is not equal to 0, because otherwise I would be dividing by 0. In this case, I would have a 0 divided by 0, so that's not allowed. A little hard to prove on your own when you're just getting started, but often you still want to deal with this sort of thing involving these divisions. So invoke this theorem and use it, move forward, and so forth. So, and then we have that. And, ooh, yeah, there's another good point. There's also Lugal. Lugal, is not as much natural language as Moogle is. But Lugal is more technical and precise if you have information about types and names and other things like that. And so there's a bunch of different ways to use this here. Great point. Great point, Rick DeWolf. All right, then let's get back to here. So, and again, if you have a theorem in hand, mouse over in VS Code to find documentation examples. This is a great way if you used ASOP, and ASOP found some lemmas. Now you can go and read about what those lemmas do. Okay. Intermission. I'm gonna just take a minute. We are going to move on to basic logic in a little bit before we get into ands and ors. So now's the time to take a few minute break, stretch, and ask any questions you might have. I did remember after showing all this stuff, I wanted to go back to this. So now that I've explained this, you can start interpreting what all of this proof means. This is the Kepler's law from Newton proof. In the have statement, there is a rewrite with hypothesis H4, but also with things like muldiv cancel, which is a theorem. How can you do this rewrite? You need to be able to understand that some things are not equal to 0 in the denominator, and you can use muldiv cancel to simplify things after you know that things are not equal to 0 in the denominator. All of there's so many different additional little lemmas proved around here with these things as well. If we had smarter tactics that could operate on things inside of a square root, for example, then it might be possible to clean these up a lot more too. Is there a grade for this class? Or is the focus mainly just to learn the lean content? Are there any assignments for this class? There are no assignments for this class, and there is no grade. It's not for credit. But I do refer you to the Mechanics of Proof textbook, which is itself a class. So, and honestly teaches a whole bunch of stuff. So, okay, in the Lean for Scientists and Engineers spreadsheet, we have actually 4 different references. 3 of these are textbooks. that have various amounts of exercises. Mechanics of proof is based on Math 2001. Let me find it again. I have too many tabs open for today. I'll just start a new one. And so here you will, so this is based on a math course that, here we go, I'll go to the landing page. This is the math course associated this is the textbook associated with Math 2001 by Professor Heather Macbeth at Fordham University. And you get the hint from the first two digits. This is a like sophomore level math course. It's for math majors, but it doesn't presume a lot of math background, which is why we are heavily leaning on this, because that's the audience we're targeting with scientists and engineers. And you can tell, like, so today we've talked about intermediate steps. We did one example, 2.1.1, but there's 8 more you can, or there's 7 more you can do, and then you can do these 3 exercises and just build your skills. So I encourage you to do the practicing. I mean, the other nice thing is, who's going to grade this? Lean's going to grade this. You know whether you get the answer correct or not. And there have been some studies, pedagogical research studies, to evaluate the effectiveness of including Lean in proof courses. For example, how does this impact student learning? And some of the comments that students taking math courses often bring up is, well, I like writing proofs in Lean better than writing proofs by hand because I know whether I got it right or not. And I know whether I provided enough detail or not. If I'm getting a paper and pencil exam and they say, prove this, and I say, like, okay, here I go. I don't know until after I get the exam back whether I got it right or not. So yeah, work through these. If you run into problems, hop on to Zulip and ask questions, and people will come help give you advice, clarify questions. Maybe next year, after we build the content this year, maybe next year we will add more science engineering specific type exercises, or problems related testing, understanding of ideas like syntax and semantics and things like that. Okay. All right, next part. Ooh, yeah, actually exercises for differential equations in calculus, we may have those. Because what we will be introducing with calculus is not in mechanics of proof, nor is it in mathematics and Lean. It's building on a thing just put together this year by Tomas Scriven. And I think that is an even more accessible method of bringing calculus and of doing calculus and Lean than the existing things. So yeah, good suggestion, but definitely extremely relevant for science and engineering. We'll have to see by the time that comes around if we're able to actually pull together these exercises, because it takes work to come up with good homework problems and good exercises. Okay, so glossary of logical symbols. You probably haven't seen these before outside of logic. These are like letters for you to learn. These are symbols that you don't necessarily see, but they're logic symbols, and they get easier to read with practice. Eventually, you just learn to see it, and you automatically translate these into and, or, not, implies, if and only if. You encounter these in Lean all the time. I mean, we were just looking at those in Mathlib, and we were seeing little things like this double arrow. That means if and only if. It means implies in both from left to right as well as right to left. Today we're going to talk about and or, and then tomorrow we're going to talk about not, implies, if and only if exists for all these aspects as well. Okay. So let's talk about and. Here's an example. Let's take P is a proposition, a molecule is aromatic. Q is a proposition, a molecule is an alcohol. And a third statement that P and Q, this would mean a molecule is aromatic and an alcohol. So the way you work through these things is, it's called a truth table. Okay, so if I'm going to say P is true and Q is true, I mean, I just said it in words. Okay, if I take these, if P, Q are true, then the combined statement P and Q is true. If P is false and Q is true, then the combined statement P and Q is false. P is true, Q is false, then the combined statement P and Q is false, and so forth. Okay. So for example, here is a molecule phenol. So this ring structure, if you're not familiar with chemistry, that means it's aromatic. The OH means it's an alcohol. So this one is, both of these are true. So this would be an instance in which P and Q is true because P is true and Q is true. I might have isobutanol. Well, this is no longer aromatic, so that makes P false. The combined two-part statement P and Q is also then going to be false. So mechanics of proof shows this. This is a simplified way of doing the, if you would, a calculation of the logical outcome. True, true leads to true. False, true leads to false, false, false. Okay. There's at its most fundamental, this table defines what and means. It's not like I'm going to say, oh yeah, everybody knows what and is. I mean, that is sort of intuitive. It's part of natural language and so forth. But the way the computer sees it, this table is the definition of and, so to speak. And so that is going to be how I understand this combined statement, how I understand this character, this upward character, that if I have a true statement about if my truth values are such and such, then this is the outcome. We would also have the or statement. And so here's another example. Let's say P means contains acrolein. I did some laboratory work during my undergrad where one of the things that we were synthesizing in trace amounts in the chemical reactor was actually acrolein. And the grad student training me in made sure that I had read the entire safety data sheet about how bad acrolein was. And if you get this on you, what are all the bad things that will happen to you? Okay. Hydrogen cyanide. This is HCN. This is also really bad. Okay. Poisonous gases. Okay. This is a symbol that is only reserved for acute toxicity. It doesn't, you're not even going to be exposed to a little bit of this chemical, you're exposed to a lot of it. I mean, excuse me. You can't tolerate a little bit of it. Like, so if you have arsenic in tiny quantities in your water supply, you're not going to die immediately, but it will lead to bad problems. If you have a massive dose of it, it's a problem. So let's just say that we have acute toxicity is the outcome. And this is an or statement, okay? I don't need to mix these. That would be an and statement, okay? I need to have both of these. This is an or statement. It is acutely toxic if either one of these is present. And the truth table is, okay, the or statement is true unless I have both of these gone. Both of these are false. So that is what, and then again, it comes back to sort of, this is the definition of what or means. It's this little truth table involved. And Mechanics of True Proof Chapter 5 goes into a lot more of these. We'll finish up this chapter on these logical symbols. I mean, I'll just jump to this one real quick. We have and, or, implies, if and only if, and not. And each one of these little tables of stuff you can study later. We'll dig into this tomorrow more in depth. We're going to get to some examples on and or in a little bit. But this is sort of what logic looks like. I think, if I might just opine a little bit, and I'll talk some more about this tomorrow, is scientists and engineers don't think about these things as much as they should. It is sort of implicitly involved in the problem solving of science. I need to think, I made this observation and I made some conclusion about that. What does that mean? Is that an implication? Is that if and only if? How does this connect to causality of experiments? One of my motivation for making a big point of this in this course is that scientists would learn the basics of these things and start thinking about them more. Can you start thinking about computerizing the logic that you bring to your problem solving and developing ways of solving these things? These are also extremely elementary logical operations. Lean is a theorem prover that's extremely expressive. Okay, it can do reasoning about infinity and limits in calculus. It's also, you might call it so inefficient it can't solve proofs for you on its own. You have to write all the proofs yourself for the most part. And there are other logical solvers which only operate in the world of these truth tables. So you're only going to do, you can't do calculus with this. Okay, but you can maybe solve interesting problems in science and engineering. If you can formulate your problem just using if and only if kinds of clauses, just using not, or, and. Okay, if you recently wrote a proposal, okay, about doing things like this, reasoning about the structures of molecules, how these types of logical statements connect together, and if we don't need lean, we can use some things that just prove things automatically all the time if you just run the computer program. And that is useful in things if you wanted to do other kinds of stuff. So we do have a question about this implies arrow. And yes, good answer from Richter Wolf. P implies Q, or in other words, if P then Q. And I don't have an example of this because I do want to get to some and or statements in lean itself, but we will get to not, implies, if and only if, exists, and for all will be all. We'll be covering those tomorrow. Okay. Back to lean. Here we go. Here we go. Okay. Here's a little fun example. Here's an or statement. We're going to do or first, and then we're going to do and. I have to make my font size a little smaller. Okay. So I have 20 minutes, and I have to make a return to a UPS store. They all close at 5 p.m. I can get to any UPS store. One is 5 miles away, and it's on the highway. Another is 1 mile away, but I have to drive local. So can I make the return in time? And I only have 20 minutes. So we're going to reformulate this word problem as either time 1 for getting to UPS store number 1 or time 2, UPS store is less than or equal to 1/3 of an hour. Okay. So we set up a little example, and I'm going to define all of these assumptions. Distance 1 is 5 miles, speed 1 is 50 miles an hour, distance 2 is 1, speed 2, and then I'm using the simple time is distance divided by speed formula. I'll just make a comment. Really inelegant example. It would sure be nice to have time defined outside somewhere, so I don't need to reuse this. I can just say, here's an instance where I'm going to define this. Distance 1 um, is not at all related to distance 2 in the sense that they're both distances. Distance 1 and time 1 are both real numbers, and there's no sense of units. So we had a question about units. Like, there's a lot of ways to make this better, but we're just sort of illustrating what OR looks like. And so the theorem statement is given here. Time 1 is less than or equal to 1/3, or time 2 is less than or equal to 1/3. And if you want to know how to type these, again, you can either find one in the literature sometime, or you can just guess things. So in this case, I can do a /or, and then a space will automatically turn it into the or symbol. And the more you do this, the more used you get to the notation. So after the by, this is my info view. Here we go. All of these assumptions, and time is less than or equal to 1/3, or time 2 is less than or equal to 1/3. So the first thing I'm going to do is use a tactic. And this tactic is left. And left is going to work when I have true or false. And it's just going to use the left side of the or. So I don't need to know anything about the right-hand side if I know that the left-hand side is going to be true. If I can prove that the left-hand side is true, then I know the whole compound two-part statement is true. If I can get to the first UPS store, I'm good. I can get there, everything is true. And so this, after the left tactic, you can see the cursor, we've changed the goal to simply time 1 is less than or equal to 1/3. We've picked the left side of the or statement. We're allowed to do that because left is using a tactic that works correctly with what or means, okay? Then we do a calc block, and this one is relatively simple. We have distance 1 over speed 1. We pull that hypothesis in, we do a calculation with substituting my numbers, and then norm num to close it off. So that's one way to do this. You'll notice that we have 3 little underlines. H3, H4, and H6 are all underlined saying this is unused. I didn't actually need those hypotheses to make any conclusion about the proof, because all I need to know is that the left-hand side of this about time 1 is true. I don't need any of the rest. So I could actually delete this and it would be, the example would still be true. Here is the other version of that, just using right. So this sets up a proof for the right side of or. We can see that now after doing this tactic, time 2 is less than or equal to 1/3. And I can just do a regular calc block to close that off using the tools we've been doing, so we have no goals to solve. So that's a way to use or, and you can see what this is doing. We're doing proof by steps. We're starting with the compound statement, we're making changes to the goal to make it easier to solve, and then we're closing it off. So here's an example with and this is going to get fun. Here we go. Kudos to Alan for coming up with this one, by the way. He's in the classroom here. He did some background research to make sure these numbers are realistic and actually correspond to skydiving, parachuting type specs. So a parachuter jumps off a cliff and opens a parachute immediately at 300 meters. His weight is 90 kilograms. He has a parachute that can provide air resistance up to 875 newtons. Will the parachute be able to handle the descending force so that the soldier lands at a safe speed? Okay, you don't want to hit the ground too fast, okay? But you also want to get there fast. You don't want to spend too much time hanging in the air. You're behind enemy lines, and the enemy sensors might target you if you hang in the air for too long. Okay. The math is simplified a bit. I don't officially know how constant an upward force of a parachuter is going to be, but nonetheless, we have 7 assumptions here. The first 3 of these describe parameters. The net resistance is going to be an equation relating the weight of this person, the acceleration due to gravity minus the resistance. So this is the net force of resistance on the parachute. We have acceleration from this, which is the force divided by the weight. I should say mass in this. That would be a correction for just in the words, but doesn't change the math of this. Okay. Then we have the time from kinematic equations of motion, assuming we start at rest. And then the safe velocity is going to be acceleration times the time that was occurring. And finally, the time must be less than or equal to 100. And the safe velocity must be less than or equal to 7. So both of these conditions must be true. It's not the or statement. You can't just get there fast enough. You die if you hit too fast. Okay, and so it's 2 constraints going on. So now here's a new tactic for you, constructor. We started defining the whole space. We have and in our conclusion. We do constructor and we split it. Check this out. This is the first time we've had 2 goals. Okay. I minimize these. You can see we have 2 goals to prove. It's not enough to simply prove the left side. We need to prove the left side and the right side together. And that's why this tactic state is really helpful. There's 2 goals. We're keeping track of them. We will go and deal with them one by one. So we have case left is given all here. All of this, along with the left goal, time is less than 100. And case right, the same context, safe velocity is less than or equal to 7. So to solve this, Alan used a calc block. And bottom line, okay, we've seen these equality-based calc blocks. We went into detail last week on how to dig into these. I encourage you to practice those. Dealing with the power to square root is a little bit messy here, but there's ways to deal with this. And so he used these rewrites and closed it all off by norm num. And now we have a proof for the first goal. Okay, so let's go after this. I guess another little clarification. I think this is helpful. I've been glossing over this. If I put my cursor right after a calc block, it says no goals. That doesn't mean I'm done with my proof. It just means the calc block, within the world of the calc block, I've closed off the goals. I now leave the calc block and voila, I still have a goal to close. So we had 2 goals up here at the start of the first calc block. Now we have 1 goal. We're making progress. We're doing great. So then we do the math, the algebra, the rearrangement, and we end with, at the end of this, no goals, closing this whole thing out. Okay, and so we got this. We're real optimistic. We've got a really fun problem to introduce to the class. And then I spotted something that we've encountered with in some other problems. 18 minutes. We're doing well. Okay, we're doing good on time. And see, if you do this little calculation here, what exactly is this thing that I'm trying to prove is less than or equal to 100? So if I just pop open Google, okay, it's 87.83 or some sort of thing. Again, lean is not a calculator, so you can't ask it to do this super simply. You have to do some tricks around that. Okay. But I spotted something and I asked my student, look what I did. I proved everything that my time is less than or equal to 2. and I closed all of my goals. But I just calculated this. This is equal to 87. How is 87 less than or equal to 2? Whoa. I got a proof I didn't prove what I was expecting to prove. And the tricky thing, and this is something to watch out for when you're dealing with number types, is you want to keep track of all of the number types that you're working with. 300 is a real number. Why is it a real number? Because I told it height is a real number. So the 300 here is a real number. 90 is a real number. 875, these are all real numbers. But this 1 over 2, the 2 is a natural number and the 1 is a natural number. Okay, but why would that change anything? That doesn't, like, if I'm to the power of 1/2 natural numbers versus real numbers, I mean, that doesn't make any sense. The reason goes back to this last point that I want to jump back to my schedule on. I ended up doing these out of order. Junk values. And why certain things seem unusual, not what we would expect in lean, in theorem proofers in general. It's not unique to lean. I do need to jump back to my lecture one and actually hunt down this slide. Oh, here we are. It's this slide. Okay. The natural numbers only contain 0, 1, 2, 3, 4. They don't contain things in between. They don't contain negative numbers. The integers contain all of the naturals, but they don't contain things in between these numbers. The rational numbers contain all of these fractions, 5/9, but they don't contain things like pi, square root of 2. These are irrational numbers. Real numbers contain both of those, okay? That's why we set up this structure like this. What does it mean, though, when I do so I'm going to use an eval. We don't use this a lot, but I'm going to show you what lean does when I say 1 minus 2. So what it's doing, 1 is a natural number, is guessing what 1 should be. 2 is a natural number, and it's returning 0. 1 minus 2 is not 0. But if instead I put this in parentheses and I said, let's make 1 an integer. Okay. Well, if I make 1 an integer, now it's going to guess from, it's going to implicitly figure out what the type of 2 is, and type 2 is going to get an integer type. I could make it explicit. I could say type 2 is also definitely an integer. Okay, and now we get an answer -1. This short expression, when they're both natural numbers, is going to return a natural number, and it can't return something negative because negative numbers don't, they're not included in the natural numbers. Negative numbers aren't here. So if I do 1 minus 2, it's going to return 0. And that's weird. And that's really uncomfortable. And it's not just that. Other examples of this, we can do 1 minus 2. Here, let me just make it clear. I'm going to call these gnats, just so you can tell what this is. I could do division with an integer. So I could do 4 as an integer. If I did this divided by 2 as an integer, all right, well, I get the answer 2. And but if I do 3, okay, I get 1. I'm not getting 4/3, okay? Because again, these are integers, they're not rationals. 1/3, 4/3 doesn't exist inside that number set. We can move on, we can do the rationals. We can go, yeah. So another example would be 5/9. Let's make 5 a q divided by, let me do some spaces here to make it a little cleaner. Okay, so 5q divided by 9. Oh, it's still taking, can I do 5/9? No, same thing. Okay, if I wanted to do 5q divided by 9, oh, well, I'm struggling to do it on the fly. We have 10 minutes left. I want to stay on track. The same thing if you try to take the square root of 49, you can do that. That's not a trouble if you're dealing with, even if with natural numbers, you can do the square root of that because it equals 7. But you can't do square root of 50. It's going to give you a number that doesn't exist in that set of things. And another puzzling one, another frustrating one that we might be dealing with is, and I should add, if you're familiar with, like, if you have a computer science background and you're familiar with like integer numbers, okay, or modulus, then you're like, ah, well, of course, it's okay to divide 5 by 3. I'm just going to, as long as I'm staying in the number type of int type in C, for example, it's going to return a 1, essentially remainder 2, essentially, so I can go and get my 1 back and I'm fine. Another case, though, that is even stranger is let's do real numbers. Let's make 1 a real number. And I'm going to divide it by 0. No. 1 divided by 0. Okay, yep. So 1 divided by 0 is equal to 0. This one is another really frustrating one because, like, what does it mean to divide by 0? If you remember from real numbers, and I go closer and closer to 0 from the right-hand side, I go up to infinity. If I go closer and closer to 0 from the left-hand side, I go down to negative infinity. It's undefined. If I tried this in Python, I'm going to get not a number. I'll have an undefined type of field here. Lean doesn't stop me. I can just go on. I get a 0 here. And we have a really helpful comment from Simon Beaumont in Math 2001. Okay, so for those of you who are following Mechanics of Proof, you've downloaded the Math 2001 repo, and you're trying these things, you get type errors, okay? That's because Mathlib 1 built guardrails around these things so that you aren't allowed to do division of natural numbers. You're not allowed to do things like this for natural, you're not allowed to do things like this because it just leads to confusion, okay? You read the textbook, you get to the latter parts of the Mechanics of Proof textbook, and you'll learn that this is the design of that. Up at the top, it would take a few minutes for me to track down, but like at the top pages in the preamble or in some of the supporting files that load up when you load the version of Mathlib that Mechanics of Proof uses, they actually disable some of these things, so you can't do subtraction with natural numbers and end up with 1 minus 2 is equal to 0. But in our course, we're only using the regular Mathlib, okay? Because the goal is ultimately to build things. So here we are. We're dealing with the messiness of 1 divided by 0 equals 0. We're dealing with the messiness of 1 minus 2 is equal to 0 when these are natural numbers. And, oh, I didn't get this into the slides, but this is how you find y is 1 divided by 0. equals 0 in lean. And you will find this wonderful blog post from 4 years ago by Kevin Buzzard, which we cited in our paper. We created an archive for this so we could have a permalink as a citation. And I'm basically going to use the rest of the time reading through parts of this blog because I think this is the pathway to become a little bit more comfortable with this, because it is weird. It is not what Python does. Python returns this as not a number. This will also get a little bit clearer when we talk about functions. We haven't treated functions yet, but you're starting to get into some more of these math operations, and you need to understand what you're doing, because here we encountered it in this proof. We proved the wrong thing. Okay, and it goes to because 1 is set up as a natural number. And when we did 1 divided by 2, we got 0. And when I then took time is equal to something to the power of 0, well, time is equal to 1. I didn't need all this business. Okay, time is just equal to 1 because I'm taking all of this to the power of 0. And so now norm num is able to solve 1 is less than or equal to 2 because this meant something different than what I intended to write in the theorem statement. So this goes back to syntax and semantics. I semantically meant something else than the syntax of this. I did not mean a natural number. As Lean understands natural numbers here, I meant this to actually be the fraction 1 over 2. We could call that a rational number. We would at least need this to be a rational number. Down below, you will see a different worked example where we change the definition of hypothesis 6 to be real.square root. So now we're using a definition from Mathlib that simply says this is the square root of a real number. Notice this is also dealing with, this returns 0 for negative inputs. So it doesn't return complex numbers. This itself, it's a function, square root. It operates entirely in the realm of real numbers. Totally works as long as your argument, x, is positive, okay, but it doesn't return error when x is negative. It returns 0 for negative inputs. Okay, so once again, we just have a few minutes. And division, and so someone is asking, is there a check in Lean where the denominator in division is 0 like other languages? Yes, for real numbers. If you're doing certain proof steps that invoke division by 0, muldiv div 0, I think, muldiv div, for example, requires that as a theorem. Okay, but let's use a little bit of time to talk about this. So, if the first thing to help make you a little bit more comfortable with this is yes, so do many other theorem provers, okay? So Lean is not special. It's not weird. It's just all theorem provers are weird. And this doesn't lead to contradictions. This just means that Lean's division symbol doesn't mean mathematical division. If R are the real numbers, okay, well, this language about functions will get a little bit more clearer when we talk in depth about functions next week. Okay, if I define this function in a certain way, I'm going to say my function of x and y is going to be x divided by y if y is not equal to 0, and f of x of 0 is equal to 0. I've just defined this function. Making this definition doesn't create a contradiction in mathematics. It's just a definition. Lean simply uses the symbol division not to mean what you had in your mind about division, but to mean something ever so slightly different than what you had in your mind about division. Maybe you thought divide, if you divide by 0, should return an error. Maybe you thought divide by 0 should return not a number, or something like that. But in general, what the point is, to summarize a lot of this stuff, is these theorem provers rely on type checking. They rely on a certain understanding of how these objects behave, and they simply behave a lot better when you define an output for every possible input that something gives. So that and it gets worse, okay? If you don't like it, okay, nat.sub, doing natural number division, okay? This is doing subtraction on the natural numbers. And it eats two natural numbers, it spits out another natural number. It always spits out another natural number. It never spits out an integer. And so either I don't even have a choice of spitting out not a number, because not a number is not an integer. It has to spit out another, not a number is not a natural number. It has to spit out another natural number. So you get to use this definition if you go and define the thing it should output whenever x is less than y. And you define that equal to be 0, and then if I want to take the square root of a negative real number, I won't use real dot square root, okay? Because I don't want an answer in the reals, and the type of real dot square root outputs a real number. That's what this means. So if I wanted to take, bringing it back to this example, if I wanted to take 2 times height divided by acceleration, if I wanted to take this to the power of, if I wanted to take 1 to the natural number to the power of 2, I need to define it differently than this. If I wanted the square root, I needed to invoke it in that way. And so let me go grab the blog post. I will paste it in the chat. I know this was such a, was my chat busted again? Come on, get me back to WebEx. Oh, there we go. And I will, so it was pretty great because one of our peer reviewers on our paper, who was coming from a scientist background, we described this in the paper. We wrote an extensive footnote about it. They had a link to it, and the person said they were when they were upset when they read this, but they made their peace with it after reading that. And if this upsets you, I want to wish you the best at making peace with it, because it's not going to change in lean. For a while, I thought about that, being like, I really don't like this, but I don't think I'm going to really persuade the mathematicians to do it differently. And no, they do it for very particular reasons. And it is more beneficial in managing these math libraries and getting theorem proving systems to work to do it this way. If you think this allows you to prove that 2 is equal to 3 or 1 is equal to 0 in the natural numbers, because you can start doing subtractions on stuff and get a contradiction like that, go for it and try. Okay, it can be a really useful exercise to try to build up that proof with your own skills, and try to develop that. If you get some ideas about how to set up a problem in order to obtain a goal, 1 is equal to true, or something like that. Can you do that? Well, good luck, as long as you don't include a contradictory hypothesis. It's like you have to avoid that, but it can be a useful exercise for you to do it, but you won't really be able to, because the definition of subtraction doesn't introduce a contradiction into math system, so that's how it works. All right, well, we are at time, and thanks for coming to the 3rd lecture. Next time we're going to talk about the rest of those logical symbols. We'll be getting into proofs with structure number 2. These get even harder than the or and the and. That's why we have a lot more time for it. Thank you very much.